Welcome to tutorial on the Butterworth filters. Okay, so basically Butterworth we're talking about was a electrical engineer who came up with two transfer functions. Okay, he just came up with two transfer functions that would suitably describe the behavior of certain filters, and those filters were known as the Butterworth filters. Alright, so I'm going to give you the transfer functions over here. So one of them looks something like this. So this is basically the gain of a filter, okay, taken as the modulus, and that is equals to, well, A0 divided by that of root over 1 plus omega 0 by that of omega. Okay, so this is one, and the other one would be the same thing, okay, h of omega, and the mod value taken is equals to A0 divided by that of root over 1 plus that of omega by omega 0 this time, and to the power 2n. Okay, so here are the two corresponding transfer functions that I was just talking about. Well, the transfer function on the left is that for a high pass filter. Now that's a filter, you might be knowing what it does basically. So a high pass filter basically lets pass, high frequency component compared to a certain cutoff frequency. Okay, so those frequency components above that cutoff frequency are just let to pass towards the filter output, and the rest are just blocked or, well, attenuated by the filter itself. While on the right we have the transfer function for that of a low pass filter. Okay, there you go. And the low pass filters, working, you might be knowing as well, is just the reverse of that of the high pass filter. It just lets the frequencies below a certain cutoff frequency to pass through to its output, while attenuating those above it. Okay, now these low and high pass filters that we are talking about having, or rather whose gain is basically described by such mathematical expressions, or rather such transfer functions basically, are referred to as the Butterworth filters. Okay, so both of these are just the Butterworth filters. Now I'm gonna go into a bit of details over here. Now we just laid down the two transfer functions. Now the question that comes is, what do each of the symbols here basically mean? Now these transfer functions, let me tell you, they are just obtained whenever we plot the gain versus frequency curve of each type of filter. So I'm going to give you the meaning of each of these variables. So first comes A0. Okay, now A0 is of course the maximum gain. Okay, that's the maximum gain experienced in the pass band of the corresponding filters. Okay, the maximum gain in the pass band. Okay, and that is basically offered by the filter circuits. And then we got omega 0. So here omega 0 basically means the lower cutoff frequency. Okay, I'm gonna write that down over here. It just means the lower cutoff frequency in case of a high pass filter. Okay, and it also means the upper cutoff frequency. Okay, just hang in there for a while. So it just means the upper cutoff frequency in the case of a low pass filter. Okay, now having said that, we also got other variables such as omega. So here omega represents the frequency of the input. Basically, these are the angular frequencies. I should write angular frequencies over here, so I just made a mistake. Okay, so it's basically angular frequencies, better off said that way. So omega correspondingly would stand for the angular frequency. Just hang in there for a while. Okay, so this is going to be the angular frequency of the input signal to each of the corresponding filters. So this is the angular frequency of the input signal Okay. And finally, we've got the last of the variables, that is n over here. Okay. Now here, n is a variable that just specifies the order of each of the filters. So this is the order for each of the type of high pass and low pass filters correspondingly. I mean the Butterworth filters correspondingly. And this n can have, well, integer values. So it basically takes off integer values, like for example, well, 1, 2, 3, and it can go so on. So these are basically the types of variables that we have over here in the transfer functions concerned. And now let me just show you how the characteristics, I mean the frequency characteristics, or the curves or frequency responses for each of the filters would look like. Alright, so here we are. So now each of these figures on the left as well as on the right represent a Butterworth filter basically. So the one on the left is a Butterworth high pass filter's frequency response, and the one on the right is the frequency response for a Butterworth low pass filter. Now you can basically see over here that for a high pass filter the response curve, okay, that's well, here let me just tell you beforehand that the h of omega actually stands for the gain. Okay, so the symbol that we've seen over here, that is h of omega, I should mention it over here, this is actually the normalized gain. So this is basically the normalized gain of the filters concerned. Okay, so as we've just plotted the graph between the normalized gain and the frequency for each of the types of Butterworth filters that we've just mentioned over here, for each of them, I mean for the high pass filter, we can see that, well, as we just go on increasing the frequencies, then its curve, okay, the gain basically increases with a gentle slope, and then it just you know, starts decreasing at a particular value, and well, moves on to have a constant or a maximum value after a certain frequency. Okay, so if we would just, well, produce a line from over here, so then this should give us the maximum gain experienced by the high pass filter. So this is going to be A0. Okay, as I said, well, A0 represents the maximum gain for each of the filter's passbands. Okay, and of course at some point right over here, okay, we'd have a certain frequency that'll be known as the F0. Okay, now we know that, well, omega is basically equals to 2 pi f. So here, since we had omega, okay, we're just taking it in terms of f. So for omega 0, correspondingly, we'd also have a frequency f0. So here omega 0 represents the angular cutoff frequency, and f0 represents the frequency, okay, of the signal concerned. So in both ways, whether you plot the curves with respect to omega or the frequency directly, doesn't matter, they'll still have the same forms as you see over here. Okay, so I just thought of plotting it with respect to the frequency directly, so that it just makes easier for you all to understand. Alright, so finally over here we can see that at this particular point corresponding to the frequency f0, we'd have the gain reduced to about 1 by root 2 times of the maximum gain. Okay, and let me just tell you, for this exact you know, phenomena is also quite the same for that of the Butterworth low pass filter, in a way that I mean the gain basically decreases beyond a certain frequency. Okay, so over here you can see that at the extreme end, so whenever the frequency, well, is very close to 0, at that time the gain is at its maximum, so that is A0. And at a certain point, well, somewhere over here, we'd have another well, point over here, that's the F0 corresponding to the low pass, I mean Butterworth low pass filter, and the gain would reduce by 1 by root 2 times its maximum value. Okay, now these frequencies, that is the F0, are of course the cutoff frequencies. Okay, so these are the cutoff frequencies correspondingly. Now for a Butterworth high pass filter, the F0 is going to serve as the lower cutoff frequency. Okay, so this is going to be the lower cutoff frequency. All right. While that for a Butterworth low pass filter, this is going to serve as the upper cutoff frequency. Okay. Now this is not our area of interest over here, but what we should actually try to find, or rather try to understand over here, is that if you just look at both the curves of the Butterworth high pass filter as well as the low pass filter, you can see that, well, if I just etch out, or rather shade out the pass bands, so for a Butterworth high pass filter, the area of the curve above the lower cutoff frequency basically represents the pass band. Okay, so for a Butterworth high pass filter, this is going to be the pass band. All right, so that's the range of frequencies that experience sufficient gains by the filter circuits, and they are just sent to the filter output. While that, okay, below the lower cutoff frequency for the Butterworth high pass filter represents the stop band of the filter. So these frequencies lying below the lower cutoff frequency are just going to be attenuated by the Butterworth high pass filter circuit itself. Okay, so I made a mistake over there. All right, so for a Butterworth low pass filter, on the other hand, the pass band lies closer to the zero zero frequency basically. So here I'm going to shade it off. Okay, so that's the pass band down below the upper cutoff frequency. So I'm just going to write that down over here. So this is the pass band, and the other one over here correspondingly above the upper cutoff frequency represents the stop band for the Butterworth low pass filter. Okay, so as I was saying, our area of interest is the nature of the pass band and the stop band. Now you can basically see over here that the pass band, okay, has a comparatively flatter response. You can see that the pass band doesn't have any kind of glitches. Okay, it just has a smooth shape, and it's most of the time the pass band is basically flat. For most of the extent of the frequency in both the low pass and the high pass filters, the pass band has a flat response. So we have a flat pass band for that of a Butterworth filter. Okay, and on the other hand, if we just take a look at the stop bands, we can see that, well, the frequency, well, just doesn't decrease that way. Now ideally the Butterworth filters were theorized to sharply suffer a drop in the gain whenever the cutoff frequencies would be reached for each of the corresponding filters. But, well, experimentally the curves look something like this. Now we can basically see over here that even at the stop band, even for frequencies were way below the cutoff frequencies for a high pass filter, and for a low pass filter for frequencies way above the cutoff frequency, we can see that the stop band is also, for the most of the time, flat. So a Butterworth filter is characterized by a flat pass band and stop band as well. So both are flat in this case. So these are the features that basically characterize Butterworth filters. So these features, I'm just going to write that over here. So these are the important features of a Butterworth filters. Okay, so this is worth mentioning over here, because that's how these kinds of filters basically get differentiated from other types of filters. Okay, now coming to the last variable of all, that's the n, okay, which just represents the order of the filter. This part is the most important. Now these curves, as I've just shown you, these frequency responses of each type of Butterworth filter was basically taken for n equals to 1. So in this case, well, I'm just going to use this blue color over here. So for this case, n was equals to 1 for both the low pass as well as the high pass filters. In this case, n was equal to 1. Now when n is equal to 1, we just call that a first order Butterworth filter. Okay, so we just call that a first order Butterworth filter. All right. Now, at that moment, whenever n is equal to 1, we can see that for a Butterworth high-pass filter, this slope, okay, the transition from the stop band to the pass band is just characterized by a slope in both the low-pass as well as in the high-pass filters correspondingly. So this particular slope for a high-pass filter would have, a rate of change of gain of about 20 decibels per decade. Okay, while in the case of a low pass filter, here the gain reduction, okay, here the gain would just reduce at the rate of 20 decibels per decade, or rather it should be mentioned as minus 20 decibels per decade, since the gain basically decreases. If you just care to plot the gain in the decibel scale, that's what you'll basically get if you measure it. Okay, now on the other hand, n is basically put equal to that of 2, then what we'll get would be a second order Butterworth filter. Okay, we'll get a second order Butterworth filter. Now for each of these high pass and the low pass filters, basically the yellow line would characterize the slope of the transition of each of the filters from low to high frequencies, and the rate of change of their gains, basically. So in this particular case, okay, for here for the yellow line, it's basically n equals to 2. So I'm just gonna write that down over here. Okay, that's gonna be a risky job. Okay, so here n is gonna be equal to 2, and for n being equal to 2, we'd have a corresponding rate of change of frequency of about 40 decibels per decade. Okay, for the high pass filter as well as that of the low pass filter. For the low pass filter, on the other hand, there'll just be a negative sign before 40. So for n equals to 2, the gain would decrease by 40 decibels per decade for a low pass filter. On the other hand, the gain would just increase by 40 decibels per decade for a high pass filter correspondingly. And then again, and finally, if n would be put equal to that of 3, then what we'd get would be a third order Butterworth filter. Okay, that's good. If you do it for the high pass filter, then it'll be a high pass filter, and for a low pass filter, it'll be just known as a third order Butterworth low pass filter correspondingly. So in that case, the red line that you can see basically characterizes the slope or the rate of change of gain for each type of for the corresponding Butterworth filters. So here, if I just write it down over here, n is equals to 3 in this case, and in the case of the low pass filter as well. So under this sort of circumstances, when n is equals to 3, that is for a third order Butterworth filter, if you just take the high pass filter for example, then the gain would change, or rather increase, at the rate of 60 decibels per decade. Okay, and on the other hand, for a low pass Butterworth filter, the gain would reduce by 60 decibels per decade. So we can basically see with the increase, if n could be increased this way, then we'd have even sharper slopes. Okay, we'll have even steeper slopes for each of the corresponding types of Butterworth filters, and then the Butterworth characteristic would just approach somewhat to an extent to the ideal characteristic that has been theorized previously. Now in the ideal characteristic, the Butterworth filters are the high pass filter. If I just give you the ideal characteristic, the high pass filter is supposed to be something like this. Okay, if you just plot the HF omega, the normalized gain versus the frequency curve, and for a low pass Butterworth filter, the idealized frequency response would have been somewhat this way. Okay, where this particular value represents the cutoff frequency. Now that doesn't happen experimentally. So in the experimental determination of the corresponding frequency responses, we get these sorts of curves. And now we can see that as we just go on increasing the order of the filters, that is n, then we can get to see that we'll basically obtain sharper and yet sharper slopes, or rather steeper slopes. Okay, now these are few of the features that basically characterize the Butterworth filters, and they are very popular in most of the electronics applications, or various types of communication circuits and all, due to this flat pass band and flat stop band response. Okay, and furthermore, the transfer function of the Butterworth filter is pretty easy to work with, and their equipments that basically follow the Butterworth frequency response, I mean filter circuits that follow the Butterworth frequency response, are, well, simpler to design. So they are basically simpler to design, and that's why they are much popular compared to other types of filters that basically exist. Okay, so with that, we just come to the end of this tutorial, and we're gonna wind up over here and see you next in the forthcoming tutorial. So till then, it's just gonna be a short goodbye for now, and thanks for watching.